Okay, physics types. A couple questions for you. Have you guys talked about work?
Yes.
In physics? So, okay, what's the definition of work?
Something requires.
Okay, there's force times displacement. Okay, work is a very, very useful, extremely useful concept for physics. Work, what is it? Okay, so work is defined in physics as technically as the product of force times displacement along the lines of force. Is that how you guys have talked about it? Have you talked about it as a dot product? As F dot S? You haven't talked about that? Okay. It's a vector dot product. And you'll get to that at some point. I'm assuming you'll do it this year. If not, maybe you'll do it next year. But it's useful because now I want you to let's talk about something. So if I'm doing work on an object, I want you to kind of understand what is that accomplishing in a sense. So if I've got this box of Kleenex, and let's say I'm going to slide it along the tray here, okay? Assume it's frictionless also. Okay, so let's say I'm pushing it along in this direction right here, and there's no friction on it. It's moving at constant speed. Am I doing any work?
No.
Not doing any work, am I? Because if it's moving at constant speed, I'm not actually applying any force to it, right? Does that make sense? Okay. Now contrast that with what if I'm moving it up in the air like this? Yeah, I am doing work then, aren't I? Right? Because I'm applying force in what direction? Upwards, because I have to counteract the weight of this thing, right? So even if I move it up at constant velocity, right, so I'm not accelerating it, that's okay. I'm still having to apply a force that's equal and opposite to the weight of the object. Otherwise it would fall to the ground, right? So I am doing some work there, and the work would be the product of the weight of this box, and newtons preferably, times however far I'm moving it vertically. Okay, now where am I doing more work? If I pick it up off of the lower shelf and set it on the upper shelf there, or if I pick it up off the lower shelf and set it on the upper shelf there.
Over there.
Okay.
That's a greater distance.
So more work over here? Is that what everybody agrees? Anybody disagree?
Wouldn't it be the same?
It'd be the same, wouldn't it? How come it's the same?
It's just a distance up.
Because I'm only taking the product of the force times the distance along the lines of force. Now the lines of force are upward, right? So any sideways motion here doesn't count. I'm not applying any force to move it sideways. I'm only applying force upwards by moving it at constant speed. Does that make sense? Everybody buy that? Okay. So then what am I accomplishing? If let's say this thing has a mass of 1 kilogram, so it has a weight of approximately 10 newtons, and I'm going to move it up 1 meter. How much work am I done?
You lost me by using all this.
Okay, well the fancy units aren't really the point, but they are important here in a sense. What are the units of work? Newtons times meters. Well, what is a Newton meter? You guys talked about this? Newton meter is have you heard that? Have you guys, maybe you're just starting this stuff? Going through it right now? Okay, so a Newton meter is what we call a joule, right? Have you talked about that?
Like a Joule?
Joule.
Oh, like it would be Mallory Johnson.
Yes. Okay, so a Newton meter is a joule. A joule is typically a unit associated with what though? Energy. Okay. Yeah, so it's interesting and important that the units of work are the same as the units of energy. Okay, so now think about this. If I'm picking this box up, it started on the lower shelf, I am doing 10 joules of work on this thing to set it on the upper shelf. What have I done to this box, in a sense?
Increased its potential energy.
I've increased its potential energy. The work that I've done has been stored as potential energy, and the proof is if I slide it off the shelf, it would fall off and do some, in physics, we'd say gravity's doing work then, the box is doing work on, maybe it's not you, maybe it squashes a bug or something, I don't know. But it does do something, right? It falls off and it makes a loud noise. So we've done some work on this thing. We've invested some energy in it that it releases when it falls off the shelf, right? Okay. Now so that very, very useful concept. Very useful concept. You can just do, you can do tons with that in physics. Okay, but sometimes to make use of this, it's nice to look at it graphically. Okay, so if we wanted to somehow take a graphical look at the story we just told, let's do it this way. And you've probably done this in class too. You've looked at work graphs maybe? Force versus displacement graphs? Okay, so let's call this axis force and that axis displacement. Okay, if the force we're applying, if we move this thing up at constant speed, we said that it had a weight of 10 newtons, right? So what is the force curve going to look like here?
Like an exponential?
Well, but I mean, so we're applying a constant force, aren't we?
Oh,
So if it's a constant force, how do we say a constant
linear.
quantity? Yeah, what kind of line? Horizontal line, sure. So this would be 10, and that's going to be 1 meter, right? That's 10 newtons, and that's 1 meter, and that's that's the story we're telling, right? Everybody agree? The force throughout that 1 meter displacement, the force has stayed the same. Do you see something geometrical about the story we just told that would give us the answer of 10 joules?
That rectangle at the
The area of the rectangle, right? This area right there, the area of that, if you think about it, it's a rectangle, and so rectangular area is very easy to calculate, isn't it? It's just height times width, right? So if I take the product of 10 newtons times 1 meter, that's equal to 10 joules. How about that? So that's a big deal. The area under a force displacement graph is equal to work. How about that? Okay. How about that? Now what happens if I take the box down off the shelf? Okay, so now we pick the box up, and I'm going to apply a force to this thing and set it down on the shelf. In what direction am I applying the force to the box if I move it down at constant speed? It's still up, isn't it? Right? But this time the displacement is down, right? So I've applied a positive force, but it's moved through a negative displacement, and so we would say then we've done negative work on the box, right? Which makes sense because we have removed that potential energy from it, right? Okay? And so if we continue our story then, I could go down, extend this axis down.
Oh.
And now we could, there's our negative 10 newtons of work, right? If we assume that the work is in the opposite direction to you can look at it either way, can't you?
Yeah.
You can either look at it as positive force and negative displacement, or you can also say what's the component of force along the lines of travel, right? Lines of displacement. And so either way, it doesn't make any difference. But if we look at it that way, then the work I've added up looks like that.
Why does it go big?
Say it again. So we moved this thing up a meter. Now we're going to turn around and move it down a meter.
Why doesn't it go under though? Why does it go over?
Well, because I could put it under if I wanted to.
Oh.
I mean, I could.
Okay.
It's fine. So what's the area of this then going to be?
Negative
Yeah.
10 joules.
It's negative 10, isn't it?
It is negative.
Right? It's negative 10 because we've got a negative 10 newtons times a 1 meter. And if I add those up, they cancel, and I end up with 0 net work. Okay, so bizarre concept, but the graph really says everything that we needed to say there is, the whole story is told in that graph. Now, it gets a little bit tricky, and not really, but I mean, just to simplify the situation for now, let's just not consider the red part of the story. Let's just look at the blue part of the story, where we're doing positive work, okay? You can probably get a sense of the value of something like this. I mean, if we wanted to, for example, do something a little more complicated, like let's say we wanted to figure out the work that's transferred to a baseball when it's hit by a bat. Okay? We could do the same kind of thing. When I taught physics in McMinnville, we had some really nice equipment. We had all this Vernier equipment, and we had force plates, and we could actually look at some stuff like that, where you can look at some impulsive collisions, and it'll measure on a really, really short time scale, like down to a millionth of a second. It would measure the real-time force curve, and so you could actually analyze the work profile of all these collisions. As you might imagine, though, something like that is not going to be, it's not going to be as nice and pretty, right? When a ball gets hit by a bat, if you look at it, the ball really gets tatered. I mean, it just gets thin, and then it rebounds, but it gets really displaced, massively deformed. And so during that process, it's not a very linear profile like this at all. There are times when the force acting between the bat and the ball is much greater than it is. Like when it first makes contact, the force really isn't that great. It's not until the ball is deformed quite a bit and elastically rebounds that you get a really much higher force acting between the two. And so the curve looks more like this, kind of. If we were to measure that, it looks more kind of like something like that. If we wanted to measure the amount of work done on the ball. Now, what's the problem with that? If we're trying to figure out the energy that's transferred, it's a curve. That's a lot harder to find the area of that curve, isn't it?
Water displacement.
Say it again.
Water displacement.
Oh, okay, there you go, water displacement? Yeah, there you go. So two-dimensional water would be helpful there. Yeah, so finding the area of that curve is a challenge, but we can see that it's important, right? Now, there are other areas where this would show up also. We could, for example, I like to draw on physics stuff, so you gotta humor me here a little bit. If we did a velocity versus time graph, okay, we could do something like if we wanted to keep track of, we have a car that's starting off at rest and it's accelerating and it's moving up to some top speed and then it's putting on the brakes and it's coming to rest. Okay? There's the picture that we have. Velocity is a function of time. Here it's at rest, here it's at rest, there it's at its maximum speed. What does the area under the curve represent here? Think in terms of units, right? It's a product of two dimensions. If I want to find area, it's two-dimensional, right? So it's going to be the product of the vertical dimension, which is velocity. It's going to be displacement, isn't it, or distance, right? So technically it's displacement. Think in terms of units. We got meters per second measuring velocity and seconds measuring time, right? And so the area under the curve is just delta x. Okay, but once again, that area under the curve would be pretty useful to be able to somehow figure out what that is. Although once again, we're met with the kind of predicament here where it's not rectilinear. And so we've got to figure out some way to add up these areas under curves. So that's the challenge. That's the challenge that calculus answers. This is the second fundamental thing that calculus does. The first problem that it solved was we were able to, it may not seem like a big deal anymore, but when we first talked about it, it probably did. We were able to find the slope of a curve, right? We can find the slope of a tangent to a curve at any point on the curve using differential calculus. Now, the next, from here on out, really, we're dealing with this issue. How do we find areas under curves? And this is what integral calculus is going to end up doing for us. It gives us a mechanism for doing just that. Okay, so let's let's look at maybe how this could work. Any ideas? Before I give you the answers, what do you think? Does anybody have any ideas? Let's say in general in calculus, we've got some curve, F, and I want to add up the area under that curve from A up to B. So I want to add up that area. Any idea, and don't try to think in terms of calculus here, but just can you think of a way that we could maybe approximate that area under the curve?
Are we looking between A and B?
Yeah.
Okay.
So the area that we're trying to find, those aren't very vertical lines, we're just trying to find all that area right
Could
in
we
there.
like find the area of like the rectangle part and then find like the
Oh.
curvy part?
Okay, so you're saying maybe if we cut it up like this, where we carve that into a rectangle, and we carve maybe that into a rectangle or something. And then that curve, we're still not gonna be able to find, but the idea is a good one, right? So, see if someone can articulate maybe more generally how we might do that. We're trying to estimate the area under the curve, which is difficult because it's curvy, by instead doing what?
Finding the derivative of the curve.
No, don't think calculus. The calculus is, the connection between the calculus you're not gonna see yet. There's no way. I mean, it's not obvious at all. In fact, it's almost like it's just, when you see it, it's like, oh my gosh, that works, and it's almost like a weird thing that it does, but we'll get there. But for now, we're just thinking non-calculus stuff, just problem solving. How might we approximate? We're not gonna get an exact answer, but how could we approximate the area under that curve? It's a great idea. Say it again. Break it up into a lot of rectangles. And why rectangles? They're easy to calculate. Yeah, that's a great idea. Break it up into a whole bunch of rectangles. Yeah.
Can you also do like a triangle as well on the sides, because it almost comes to.
We could do, if we could make some triangles out of it, we could do lots of things. Okay, now there's kind of a balance we gotta strike here though. Now think about this. We'd like to come up with, as always in math, we want to be as systematic as we can. We want to come up with a way that we can repeat for different situations, right? Different kinds of curves, okay? And so, true, we could kind of look at this and customize it and say, okay, well, for this curve, that fits, and maybe I'll put a triangle there and a triangle there. Except if we have to do that every time, that's going to be extremely tedious and very time-consuming. Right? So is there a way we could come up with just kind of a general strategy here where it just works the same every time? But the idea is a good one. How about if we cut them all vertically, for example? Right, great idea. So let's do, what if we just cut like slices vertically, and we'll just approximate, so like this one right here maybe would be, will you tell me where I put the tops on these things?
Just connect A to B horizontally.
So just like those two right there?
Yeah.
Okay, like that?
Oh.
Hey, that makes sense.
Okay, now it's not perfect, is it? But it's not bad. If I added up the area, it's gonna be a little bit too big or too small if I add up all those green areas. It's a little bit too small, right? Now, what have we really done there? Well, we found what's called the inscribed, we've estimated the inscribed area. Okay, we've taken all these rectangles, and it's a really good idea. You guys come up with a great idea. It's almost like we're pushing up these rectangles from the bottom until they bump into the curve, and then we stop, right? So we always know that the area is going to be a little bit too small. There's going to be that extra little bit up at the top that we didn't account for, right? We could add all those up though, and to make it even easier, what would you recommend we do with the widths of those those rectangles? Make them all the same, right? Why not make them all the same? And so if we know that we're going from A to B, where A might be 2, for example, that's a terrible 2. A might be a 2, and B might be a 6. if I'm gonna make all the widths uniform, let's just say, for example, that I'm gonna cut it up into 4 rectangles. Then the width of each one would be 1. If I make it into 8 rectangles, the width of each one would be 0.5, right? It's just this total width divided by the number of rectangles, right? You getting the idea? Okay. Well, that's an underestimate, though. Wouldn't it be nice if we could maybe get a corresponding overestimate, and we could even just average the two? How can we do that? So we've got this underestimate. We know that when we add up the green area, it's gonna be a little bit too small. And if we always make our estimates to be the inscribed rectangles, the one that we're pushing up from the ones we push up from the bottom until they bump into the curve, we're always gonna get underestimates.
Yeah.
Make them taller. How much taller?
Instead of
Just like where they meet at the top, like joint cross.
Ah, okay. Okay, so what if instead, let's make some purple rectangles, and the purple rectangles will be tall slices, and we'll just shrink them down until they hit the rectangle on the, as they're shrinking on the bottom, right? Does that make sense? So this first one then would look like that. See what I'm saying? So we're gonna shrink it down until they hit,
a lot of colors.
right? You get the idea?
Yeah, oh yeah.
Okay, so they're all just gonna be a little bit taller. Right? And those are gonna be overestimates, aren't they? But they're just as easy to calculate, right?
Yeah.
Now that's what we call the circumscribed area, the area that's just outside, that just encloses the curve. It's not gonna be perfect, but then if we really wanted to get an accurate estimate, we could add up the green area, add up the purple area, and do what?
Yeah.
Just average the two, right? And we'd get a pretty good estimate. Okay, so that's one strategy we have. One strategy we have is adding up inscribed areas and circumscribed areas for really simple areas to calculate, for uniform width rectangles, and average the two, okay? I've got a little applet here that illustrates this. Okay, so let's just take something like this curve y equals x squared. Okay, and let's try this. Let's go from, well, we'll go from, how about from 2 to 6, like we just said. Okay, so there it is. Obviously, it's not drawn to scale. The vertical scale, you can see, is a lot more aggressive than the horizontal scale. But it gives us an estimated area of 54 if we do that. And that's really easy to calculate, isn't it? I mean, we can, how could we find the heights of all those? If we're going to go from 2, starting at 2, it's a little bit misleading. We're starting from 2, and so really the y-axis is over here. From 2 to 6, how could we find the height of that first rectangle?
Just look at the y coordinates when it has the x.
Okay, so it's defined, isn't it, by that point right there? Agreed? Okay. It's defined by that point right there. Now this curve, remember, this is just the function f of x equals x squared, and this is an x value of 2. So what's the height of that rectangle going to be? How'd you get that?
Put it into
Okay, it's just going to be the value of the function there, isn't it? Right? The coordinates of that point are just going to be 2 f of 2, right? So 2 and 2 squared, right? What would it be out here at 5? How tall is it? 25, right? And the widths are all 1, and so we can add those up really easy. The area of this one is just 4 times 2 is 4. How high is it here? Yeah, this is just going to be the point 39, so it's going to be 9 times 1 is 9. This one's going to be, that's at 4, so the height is 16. And this one's going to be 25, so we can see pretty quickly how we get 54 for an area. Just add up those numbers, right? So it's an underestimate, like we said. If we look at the corresponding overestimate, that means we would, notice it says taking samples at the left. What that means is the height of each rectangle is defined by the left edge of the rectangle, right? Everybody see that? Because remember, we're inflating the rectangles from the bottom. They're inscribed. And this is a function that is monotonically increasing, meaning it's increasing always, right? Over our domain at least, right? And so if it's increasing always, doesn't that mean that the left edge is always the lowest edge, right? Okay, so we'd have to use the right edge then to create the circumscribed rectangles, okay? So let's do that. Let's pick the right ones. And now we get an area of 86. So if we were to average 54 and 86, what do we get? Somebody, what's 54 plus 86 divided by 2? I bet it's about 70, huh? I think it is, isn't it? Yeah.
69, 70. There's
70.
actual area under it.
Okay, so the actual area is 69.33 repeating, right? 69 and a third. So that's a pretty good estimate, isn't it? Right? Now, what are things that are going to erode the hey, how's it going in there?
We have one student that is not showing any courses, so what do we do with that?
They've got to log into Moodle and enroll.
Well, he tried to do all that, but no, he tried to log, so she's logged in,
Uh-huh.
but it doesn't show any courses.
Recording it. What are some ways that we could, can you think of a way that we could try to mess this up? How could we come up with some curves that would make this maybe not work quite as well?
Obviously do wouldn't it?
Yeah.
Domain, it's the same number.
I mean, what happens, here, tell me why this one's not going to be as good. I'm just going to pick a different curve here. Let's go x to the 6th, how about?
It's too extreme.
Ah.
Actually, it gets so big.
Okay, because it's a really extreme curve. Yeah, so it's a very aggressive curve. It's a very curvy curve in a sense, right? And so this, read anything into that, please. And so look how far off we are. The actual area, let me make this a little bigger so you can see maybe a little better. Okay, look at that. We're way off, right? And we're also going to find that this one is not as symmetrical. If I use the left examples, it's not as bad an estimate. It's still bad, but it's not as bad an estimate. If we average the two, we're not going to get a great estimate this time. Okay, so it has its limitations, doesn't it? Okay, let's go back to an easier one to deal with. We'll go back to x squared, and let's even make it easier. Let's go from, for now, let's just go from like 0 up to 4. How about? So we're just starting right at 0. That makes things a little bit easier to see. Okay. So one way that we found to combat this was to the inherent underestimate or overestimate was to average the two. Okay, and that worked great for this. Not quite as well when we used a more aggressive curve. Anybody have another idea how we could get a good estimate? What do you think?
So with the rectangles, instead of like cutting them on the inside so it's an underestimate, or cutting them on the outside so it's an overestimate, just draw a point right in the middle of the rectangle.
Okay,
And
so
make that as the top, so that way there's like a little bit of the left and the right, so it cancels out.
okay, we could do like a midpoint. The midpoint is going to be more accurate. No question about it. It's going to be more accurate, isn't it? It's if we go to x to the 6th, you're still going to find, look at that though, the actual area is still quite a bit off. It's pretty similar to what it would have been if we had averaged the two. So even the midpoint, it's good. It's a good idea. That's one strategy. Okay. What's another one? Any other ideas? So say we're going to stick with like left and right just because they're so easy to do. If you're using the midpoint, then you have to find the midpoint each time, and that adds an extra step. A little more complex, a little more time consuming to find our areas. What's another thing we can do to increase the accuracy of our estimates here? We can average the lower sum and the upper sum, we could call it, right? Inscribed and circumscribed. What else?
Could you draw a triangle
Well, we could, but then that's going to complicate things. We don't want to complicate things. We want to keep the same general process. Okay? But is there just something we can do about the rectangles that we're just going to use rectangles, and we're even going to measure them on the left or the right. But is there something about the rectangles we could do that would make this more accurate? Make more of them. Yeah. Watch what happens if we make more of them. Instead of using 4 rectangles, let's use 8.
Oh, cause you're,
Oh, yeah, look at that.
gotcha.
That's much better, isn't it? Much better, right? Everybody agree? Okay, a lot better. And why stop at 8? If I try 12,
20.
look at that. And there's no reason even to stop at 12. Why not do 100?
Kendall, just, wow.
That works.
Okay, look at that. That's getting much more accurate. And really, there's no reason for us even to stop at 100.
Go to 1,000.
There we go, that's at 1,000, is Nick.
It looks the same.
Now, it takes, I don't think it's actually done it. It takes a while probably to.
Oh,
Okay, it's getting,
it's still not there. Go to 1,000,000.
$1,000,000.
it's taken, even for Mathematica, which is a big-time computer algebra system, and this is just the online version, but 10,000 is going to take this thing a couple minutes to calculate probably. Because that's a lot of areas to add up. Okay, but that's a powerful idea, is the more rectangles we have, the better off we are. And so if we can just add some tools here that will allow us to do that, that would really be nice, right? If we can come up with a way that we could do this very regularly and somehow come up with a method for adding up a whole bunch of rectangles. Obviously, we can't add those up manually, right? That's going to take way, way, way too long. Did it break it, probably? What did it say?
Didn't say anything.
It just broke. We just broke it.
Down
Yeah.
Nick,
We just broke Mathematica. Okay, so what are some ways that maybe we could do that? Let's explore this a little bit. Let's start with. Let's just get a little bit of. Here's my idea, just so you kind of know what I'm doing. So if you know what I'm doing, you'll understand where this is going a little better. We're going to take easy functions, and there's a reason I'm not doing easy stuff just because I don't think you can handle hard stuff. You can't. But the reason I'm going to do easy stuff is because we're going to stumble upon an idea here that's going to really be so revolutionary that the easy problems and the hard problems end up being just as easy to do. Okay? So we're going to figure out our techniques. We might as well just focus on the easy ones. By easy, I just mean functions that are always increasing or always decreasing. That makes things a little bit easier to deal with. Okay? But my idea is, let's just, and we're going to run out of time here today, but we'll just pick up with this tomorrow. What I want to do is we'll just start off calculating some manually. We'll just, by that I mean I'll just give you some, maybe x squared or something, and we'll just go through and we'll calculate inscribed areas or circumscribed areas manually, starting at 0 or starting not at 0. And then the goal is, let's see if we can come up with a formula for doing this that's going to not require us to change our thinking for every different function that we use. Okay? So, I mean, there's no sense, aren't we out of here at 40?
Yeah.
Okay, which is like in 2 minutes on this clock. So there's no sense even really starting one, but here's what I want us to be able to do, just so you get a little glimpse into the future. I want us to be able to say, we're going to start at A, and we're going to end at B, and we're going to cut this thing up. Let's say we're going to do inscribed, not that it really matters. So we're going to be able to just add these things up, saying that we've got a total of n rectangles. We know the width of this thing, and we're going to estimate an area based on where we start, where we end, and the number of rectangles. Okay? And we can do that. Okay? That's our goal. And tomorrow, that's what we're going to walk away with. All right.
Try to walk away.